Sorry about small problems. I'll have to get... Hello. Hello everyone, and today we will be streaming about this Advantest R6581T voltmeter. So it will be interesting project to repair, and I have to fix the video feed now, so hold on with me for a second. Okay, I hope video is working. Yeah, it looks like it. And yeah. Let's get rid of some labels. Well, or I can just tape them out. So the original problem with this unit is absent display image. So we'll see if we can get that fixed, and then we can go ahead and check other things on the rest of the instrument. So first I can show that front panel right over here. So it says previous calibration date was 1999 and next is 10 years after. There is nothing on this label. And the front panel looks all clean and nice. And driver chips have the date code 1998, work week 44. So I already, well, we can do it again, but I already took the screws off and checked the vacuum display glass, and it's all good. It's not damaged. There is still vacuum intact, so I'm pretty confident that this board is okay, and we have problem with the unit itself. So we'll put this aside for now. and go ahead check other things. And here's the digital board. I already take it out because I was doing some checks. And here we have. Nice and clean. No obvious broken parts. So firmware, this is the firmware A02, same as other units I saw on the internet. You have the main processor, expansion memory card, port, and some PAL scales. And this is expansion card slot. That's main switch. Have some regulator in here and the battery. The battery used for RTC and probably for calibration constants. And we will check the battery. So that's, and there is the front panel connects to these two green, or they are more like teal color connectors. There are two fuses in here and high voltage supply in here. So we'll have to check all that. So we'll put this board aside. And the instrument is same size as 3458A, but not so deep. And it's aluminum chassis, much more lighter than 3458A. So we'll see how it goes. It has some interesting design concepts and ideas. We will look about those in a minute. And on the rear, you have mains input, switchable with 110 or 220, fan, rear connectors, a trigger, complete measurement complete output, comparator output, GPIB interface, and option slot for the analog output card or the scanner card. So it's rather nice and compact unit. You have the legs on the side, so it can be put vertically. So we can go ahead and remove the cover. Oops, sorry about all the noise. It's a little bit too big for my small bench. I hope the sound is okay and there is not too much background noise. Today in Taiwan is a holiday day. It's a national holiday, so I'm doing this live stream in daylight, which is unusual to me, and hopefully we will be streaming for a couple hours. I have a couple other projects in background to do too, but we will get to those some other time. And I think I need to find a better screwdriver. So yeah, this will do. There are just two screws on the rear to remove the cover. Here we go. I'll put the screws in a box so I don't lose them. And then the whole thing will just slide in and slide out. just like that. There are like plenty of vents for the on the front. Here is the fan air inlet. So that's it, and some legs. We'll leave this thing aside. So you can see already its design is very similar to 3458A. So you have the digital board down there on the under the transformer. Then you have interface board, which also have the optical TX and RX transmitters using the fiber to go into the in-guard section. You have the mains transformer, and then you have the secondary transformer over here. And then you have fan, small 40mm fan. And unlike the 3458A, the fan airflow is going out of the instrument. So you have the air coming in here, going through the digital board, cooling the transformer, going into here, and then going back on the rear. So we can take, and you can see this box with the analog section. So this box is actually suspended on those isolation spacers, because this whole thing can be driven by the guard voltage of your input signal. So you will have no leakage or capacitance to the exterior case. This is required to maintain the high isolation and avoid the excessive noise from chassis and earth to go into the sensitive analog circuitry. So we can remove this aluminum shield, and look at that. Nice and compartmentalized design. You have secondary transformer, DC supply from and rectifier from transformer to the output, and then you have single analog board. And this unit have only DC voltage and DC current functions and resistance. It doesn't do anything AC. So you don't have extra board, which is AC board, which sits on top of this one. Right there in center we have the hybrid, ADC hybrid. Then you have input relays, switching, all that. The voltage reference over there, it's on the separate module. And a lot of other auxiliary connections and circuits. So I'll move the unit a little and we can take a closer look. So let's move the camera just a little. So there we go. Here we can see the DC voltage reference. This is LTZ 1000 circuitry, and it is based on reference design from Linear. Like, no wonders here. So, but it's actually better than one used in HP. It's set to the proper oven temperatures, not scorching hot 95. And using the hermetic Vishay, well, this time it's Alpha Electronics resistors. And newer Advantest units had replace some of the Vishay resistors from hermetical type to regular. But this unit is made in 1997 and still have hermetic resistors there. Very nice and clean. Probably we can take it away to take a look. There is no screws, is it? Or, oh, probably it's screw from the bottom, because I can see the threads going from here. So we will do that next time. But I plan to test this reference and compare to one of my HP references to see what's the temperature coefficient and how stable the output is. I think it should be all good. And I can take a look for my HP A9 reference to show you and compare, if I can find it. Well, maybe not. I can show one of my own designs. So this is the size of my own DC volt, 10 volt DC LTZ reference. It's quite bigger, but not that much. And here is my old KX version, which just output 7 volts. So the next to it we can see main shunts. Yeah, so these blue resistors, this hermetic resistor, this like TO220 looking resistor, and this big black one are the current shunts for current measurement function. And you have the relay to tap on each of those resistors. And probably relays actually for other circuitry. I think it's all switching could be done in solid state. And then you have all these colorful common mode rejection filters, everything very nice and clean. You have also big relays over here. Those probably for high currents as well. Then you have some other stuff. This is obviously the ADC hybrid. It's custom made by Advantest, and the claimed linearity in performance is similar to 3458A. So we'll be checking that after we get the unit fixed. That will be interesting and very long tests. Then you have here optical insulation. So this is some auxiliary interface which comes from this ribbon cable, and then the main transceiver is these two black fibers going into these transceivers. And then on top of that you have ohms current source and ohms circuitry to generate stable currents into unknown resistor connected on the front of the or the rear of the instrument and measure resistance. And then the DC regulator board is right here, really compact, and you can see all the air is directed by this shield, so it's all nicely thought. And another benefit of this unit is that it have also rear, front, this is rear, this is front inputs, and it can be switched using the relays remotely from GPIB. That could be useful. For example, if you comparing one resistor to another, you can use switching front to rear without swapping cables or messing with the instrument front panel. Similar design used in other meter, used in metrology, like Fluke 8508. Alright, so let's go back to the digital section. So we have the mains going to this big transformer right over here, and then we connect one. This goes to DC board, this one goes to the secondary transformer, and the interface board is connected by a ribbon cable. So what I think I'll do, I'll take the transformer away so we can connect the power without having to mess with anything else. We will troubleshoot the unit step by step as the progress continues. So to avoid any accidental damage for analog stuff, I'll put the cover back in. And like from the design overview of this Advantest, it was designed later than HP unit, but you can clearly see a lot of ideas were borrowed or, like, let's say, reinvented in this unit. So it's kind of will be very interesting to compare one of these Advantests against my HP stash. And as you can see, I also got the nice fancy DGK ruler. So I didn't ask for it, it just showed up a couple days ago. Kind of cool. I guess that's the, as one of my friends said, subtle way to remind that you are spending too much on DGK. Alright. So let me get some parts out. So you can also see the design is very nice and clean. All the wires nicely fixed. Everything very nice and clean. So I think I'll try to disrupt it as little as possible. But obviously I'll have to free these cables over there. The problem is why I have to remove all this, because this board sits right there. And I'll likely need more access to this area and that area for probing and for testing than I currently have. So it will be just much easier to remove what I need and do the testing with the boards standalone separately. That one is okay, that one is okay. We don't need all this. There we go. Now I can leave the unit just standing on its side. And I have some room to work on the bench with the ability to probe things. I need some more light. There we go. And also I can have the front panel board. I think I'll take it out so we can have board sitting right in here without risk to damage FPC cables. There is no any visible damage or any visible blown components on any of the boards, so hopefully the repair will be easier. But as usual, you never know. The front panel is also completely aluminum piece, and actually I'll try to show, but have a very nice touch. There is a metal braided, there you go, metal braided wire going all over across the whole panel to couple with the case shield, and very good insulation. This is very commonly seen in different RF equipment, but it's a little bit unusual to see it in DC voltmeter current meter. It's a nice touch. And the front panel, I can see the marking on the PCB. It's 4-layer board, and the digital board is 6 layers, and analog board is 4 layers. You can see also a lot of like paint marks on all the ICs. Those are marking for quality control. So now we can carefully take the front panel board. There we go. And indeed you can see very nice dual line display. It's actually very similar to one used in Keithley meter. Sorry about the flare. Let's actually compare, because I have one of the dead glasses from Keithley. It could be even same manufacturer, so here we go. You can see the Keithley display is a little bit larger, just a little, but overall it's almost the same thing. And it does have all the external drivers and everything. So just a grid of arrays and columns. So all the buttons nice and not sticky, everything all right. You can see the provision buttons for AC function, these 3 buttons, because obviously the full full function meter have those buttons populated, and you can see it's copyright 1994, Advantest Corporation, made in Japan. So there we go. Also, what I like about this glass, that it doesn't have the vacuum port, at least not visible from any of this side, so it's a little bit less easy to damage. So okay, enough for that. And the front panels just have metal shield with a window, not much going on here. Okay, so let's check the battery and see if it's any good. Not that it really matters at this point. And another very good thing about this Advantest, that unlike most of the other meters, actually all of them except the 3458A, this meter have the auto calibration function, just like 3458A. It's another common thing between them. So that means you can use only two input signals, 10 volt and 10 kilo ohm, to calibrate all the functions and all the ranges of the instrument, which is very nice. That means you don't need to use calibrator source like Fluke 5700, which is extremely expensive, to adjust and calibrate the meter. Alright, let's check the battery. So we have one terminal, and as you can see, it's dead zero. No life in battery. It still have some Japanese markings on it, so I guess it's original battery, and it's long overdue. I don't have a replacement for it at the moment, but well, we will find something to bodge in there for the tests. Right now I don't think it matters. What matters is that we connect this connector over here. And the cable connection for the front panel board is this flat, flexible PCB cables, which are, and these connectors for them, which I really don't like. They're easy to damage and hard to replace. So I'll have, probably I will do that now. I'll check that every single conductor is okay, just before we go to the rabbit hole and start repairing instrument which isn't faulty in the first place. So for this testing I'll use good old Fluke 87.5. This guy, which is have very fast continuity mode. I'll probably put it like like that, so you even can see the screen. So let's check each one. So I'll check them across the length that they make the contact, and also one between each other, so there is no short. This shouldn't take much time. All looking good so far. All right, this cable is good, and we can mark it as so. There we go. Now we can test the second one. There we go. All right. This is kind of bouncy. Let's tape it down a little so it doesn't move too much. And indeed, in the chat box, somebody corrected me. I mentioned that auto calibration is present only in HP3458A and this meter, but actually there is another Advantest meter. It's the AD-CMT model 7480, and it have a lot of carryover over this design, so it's used the auto calibration function too. Uh-oh. I failed because the contacts are from the other side. And I'm testing this cable because it's not very rare to have the cable damaged, like you have a small tiny crack on the side and then the conductor will get open, or it will be like sometimes open, sometimes closed. so it will be a pain in the ass to troubleshoot. Okay, the cable is good. Which is a good news, because this would be hard to replace. Let's put the nice happy sticker on it. There we go. So what we can do now is to check the input power. And we can check the output power. And for that, obviously, I'll need to supply some power to the unit. So let's check, make sure that there is nothing conductive on the bottom, that everything connected nicely. Switch is off. I don't think we need interface board at this point, but we can plug it in. There we go. And the better way to be is to check all the power rail resistances, to make sure that they are not shorted. But I think I'll just go ahead and turn it on. So the mains input selection switch is indeed 120 volts. Now we are live. Here I have the mains cable going over. And we can check some AC voltages entering this connector. I can hear the fan spinning. So, and I hear the beep. So here we have 2.6 volts. Here we have another 2.6 volts. Here I have 42 volts. And here we have 7 volts. Now we can check digital voltages. So for that we will switch to, this is the ground point, TP22. And there would be, I saw somewhere 5 volt point. Let's look for one. There's our reset. Oh, I'm sorry. So auto range. So reset is, well, okay, stupid me. Reset is 5 volts, so its unit is not in reset. That's promising sign. Let's see voltage on the fuse. Okay, there is some AC voltage. That's likely the filament. Okay, 41 volts. Looks okay now. and this is AC 2.6 volts. However, this is AC 41 volts. I'm not sure if it's correct. I think the VFD drive should be DC high voltage and AC filament. So we can turn the unit off, connect the front panel board and test again. So I'll think about how to arrange everything, because these flex cables, they will not bend in angles. They can bend only like this way. So I'll probably rotate everything 90 degrees. So we can have the front panel board and unit itself and the digital board all secure in comfortable position to work on. So let's do the rotation. As you can see, I'm extra careful because I don't have the replacement for that VFD board, and I don't think it will be any easy to find. So there we go. I blocked the light a little, so let's get it all in the way. I can give you overview. So it's unit standing on the side, and we have all the other stuff. This should give us enough room to work with. Now the VFD board will go right on top, and here we'll connect to these FPC connections. Okay, let's get the mains cable in. And hope that there will be no earthquake to ruin all this contraption. Actually, recently there are plenty of them, but I'm not in the East Coast area, so while I'll feel them, it's not as nasty as in those areas. Okay, here we go. All nice. Let's connect these FPC cables. and they go like that. Nope, that's not very good. I always hated these latches on them. Maybe I just don't know how to cook them properly. Oh, actually this connector is broken. It's missing one side latch. Alright. I hope I can buy some replacement for the connector. And yes, this is correct side. Maybe I'll connect from the board first, because they have already pre-bent angle, and that might be helpful. And since I don't want to damage the glass, just put this towel. Okay, so this goes like so, and this goes like so, because this one have smaller bend radius. Yep. There we go. One in. There is another one. And you can see they plug all like that, and there is not much extra headroom. So okay, this cable in place. And yes, I'll definitely need to take care of that connector, so we can check that nothing touching the board. And do the quick power on test. So there is nothing on display. and there is no beep. You can turn off the light to indeed confirm there is nothing on display. All the cables nice and firm. Yep, nothing. We can check the voltage. As we before were measuring AC voltage on those fuses. Let's see if it's still there. There's the ground, there is the fuse. 2.5 volts, 41 volts. But the other side is broken. That one is okay, and another one is there is no voltage over the fuse. What that tells us? Well, that something blow up that fuse. Let's check if we have short to ground on that fuse side. Maybe it's some driver took too much current and destroyed itself. So there is 1.5 mega ohm. And this is the main side, so there is nothing there. All right. That could be too easy for repair. So let's take the fuse out and replace it. Now the fuse is, let's see if I can see any marking on it. It's a nice little SMD fuse. Probably I can change the lens and to show you in better detail. So give me a second. All right, there we go. So there you can see this fuse, the far one, F2. We measured at 2.6 AC voltage. That's the filament drive. And this fuse, F1, is measuring 41 AC from this side and around 0 from that side. All right. Let's take the fuse out and replace it with some bodge. Because I don't think I have the fuse of this size at this moment, so I'll have to make DigiKey happy again and buy a new fuse. This looks like one of those little fuses. And it says, what does it say? 315 mA, so that's 350 milliamps. I can probably show it to you more closer. Get my lens focused. There we go. That's the bastard. So I get something similar for the same current, and we can try again. Looking for the fuse. If you guys have any question or want to ask something, not necessarily about this specific meter, let me know. Do you think this will work? Probably not. And currently I'm located in Taiwan. I live here 7 years already, but actually originally I'm from Ukraine. And I work in computer industry, designing graphic cards and motherboards and stuff like that. I'm sure I had some suitable fuses for that. You can probably hear me going through the boxes and stuff. Come on, I just need one little fuse. Well, I found one that is rated 0.5 amp. Found one that is rated 1.5 amps. No? Yeah, well, probably I'll use one of these for now. So I found this guy, 500 milliamps, and I bought them for another project, but it's small enough to fit in there. So it's this little guy. Should be good enough. It had just 2 legs. So we'll just bodge that in. And yes, I work at TVJ. Okay, let's clean the mess. For that I'll need the IPA over there. I just like everything clean. Now we can put the fuse in. There we go. So the bodge is in, and there are 2 things that can happen at this point. One, either everything will be working fine for the display, and the second is that the driver, one of the driver chips, could be dead, and short the fuse again and kill more stuff. So let's see what happens. I'll turn the light off, and yes, we have communication error, and it's very dark and faint. I'll probably have to turn all the lights off, but it's there. It's there. Let's try that. Now it's completely dark. Well, almost completely dark. And this is totally normal because we don't have the analog board or anything connected. So the in-guard CPU tried to talk to out-guard CPU tried to talk to in-guard analog section. Doesn't hear any response, and it goes communication error. Let's check the voltage. I want to make sure that the voltage is fine. So here's the input. Well, I need to use the AC. So it goes to about 19 volts AC. I'm still not exactly sure it's correct. I think the drive voltage for VFD should be DC. Let's turn everything off and check if anything gets hot. No, they are all nice and cool. So I'll have to investigate into this a little bit further, or maybe have somebody who have one of these units working to measure the voltage for me, if it's DC or AC, because maybe it still should be like 40 volts DC. Then probably one of those driving rectifiers or DC AC/DC generators is not working right. That could be also the reason why the display is dark. But I know what you all guys want. You want to have me everything put together and see if the meter is actually working, right? Let's crank the lights back in. All right, let's put everything in and see what's going on. I'll also put the front panel into its metal case, because I don't think we have much to troubleshoot in here on this point. And somebody was suggesting to use 2400, that is Keithley to 2400, to source the voltage, but my 2400 right now is this box. It's have a little bit sick of the front panel plastic, so the front panel sits separate. As you can see, it had little better days. So I'm waiting for the replacement for this, for front panel plastic. The electronics and everything works fine, just need the plastic. Okay. Oops. I would laugh if all of this unit problem is the bad fuse. But I don't think we are lucky so much today. Or are we? Alright, front panel all nice. Everything looks very clean. Let's put this aside for now. And get everything going in here. Disconnect the mains. Okay, everything turned off. Also, what I think that beep was when we didn't have anything connected to digital board is that it detected no response from front panel, and then it give you alarm about that, like, oh, we're missing hardware, put it back, something like that. As you can see, obviously at this point, we probably didn't have to remove the transformer or anything if I would check the fuses first. And the reason for that is I thought I checked the fuse before, when I was just getting the unit, and I thought they were fine because I'm used to measure DC voltage. I knew that usually VFD uses high voltage DC for segments drive, and there was no DC voltage, so I thought, like, okay, there is some problem with the high voltage circuitry, so we have to remove it. But as we see, it's just me lacking the knowledge that it's could be the AC drive, which is happened before in other instruments, but I'm just not as familiar with it. That's okay, at least we looked different way on the things, and it's not much problem to remove 2 screws and transformer and put some zip ties. I can put carefully put everything. And indeed, I like that the chassis is aluminum, because it's much easier to deal with and much lighter, and overall doesn't corrode like my good old rusty 3458A. And those guys just... there we go. Nicely designed. You can see this high power part is heatsink, and use the cases as a heatsink. Very nice thermal thinking to keep it nice and cool. Oh, my bad. It's not going in there. This screw goes over there. Whoop. Where did you go? Okay, all screws are in. I think I forgot this thing. This thing goes in here. So I'm not sure that's correct screw for that place, but whatever. Oh, and also battery. We will have to replace battery when I get the suitable replacement. But for now, probably shouldn't matter that much. We already know that if that battery used for storing for power and memory that store all the calibration, that it's already all gone. So no point to worry about calibration now. To remove the screws for front panel. That's why I don't like these cables. Maybe it would be easier if I do it like that. Yes, it's a little bit easier. I should have connected the bottom one first. Go in. There we go. Okay, the cables are in place. Now we can put it all together. Just like so. I forgot the power button. Let's see. And okay. Let's see if I can put it in without removing the front panel. It's nice and clunky switch. Now this soft button rubbish and stuff. Oh yeah, so all goes nicely. Okay. Also, the front panel is much easier to assemble and put it in than 3458A. Doesn't need any force. Just lock by 6 screws and one more screw to go. And okay, check connections. All looks okay. So let's turn the beast on and see what happens. Wish I would have some way to lift it, but nah, okay. Just didn't want to move the camera too much. That's alright, I guess. go. Nice and in focus, hopefully. Are you ready for the smoke test? And I need longer power cable. All right. Communication error. I know why is that happened, because I disconnected the supply from the analog part, because I wasn't sure if the transformer is okay. I didn't want to supply a lot of power or some wrong power into AC section. So we can do the check now. I'll put the meter over here. And we can measure the transformer voltages. There should be no high voltages here, so, but I'll be still careful. So we have 30 volts, another tap, 30, 17, 7.5, all looks good. I'll connect to the regulator board, and I guess we'll see what happens next. And still communication error, because I didn't plug that small ribbon cable with the blue 10-pin connector. And it's paying to access now. Okay, I think I can get to it. Let's go, little fella. There we go. Now it's plugged. So this cable connects to here, to that interface. Yay! Beep. Okay, so there is some craze going on, and I'll have to show you in a moment. Because the VFD is so dark, I have to do this adjustment. And turn off the lights again. So, as you can see, the outer range function goes crazy and switching all the ranges. So Okay. Let's see if we can go range down. Up, 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 up. Outer range, and it's blinking like mad for all the ranges. And high voltage ranges show overload. Now we can supply 10 volts and see what happens. I'm sure nothing good will happen, but that would be a good final for this live stream. Maybe. Or I could go on and do more tests. Yes, we can do a short first. So let me get a cable. So I'll connect the short. Okay, so the short is working. Let's check out the ranges down. Okay, this is the lower ranges not working right. And the high ranges is not working right. I think it's because some digital communication. I mean the comparator which sets the ranges not working. So, and 10 volt range is base, so it's going direct to ADC, like through the input amplifier without any gain. So we'll have to troubleshoot that. Let's check the 2-wire resistance. Okay, it shows overload. Oh, so 10 mega ohm range shows 0. 100K shows 0. 100 ohm. And this one. So only a couple ranges work on ohms. 4-wire. Oh boy, that's the current. The relay go crazy because all the ranges change. We don't go there. So let's check 10 volts. And for 10 volts I can use the beast right behind me. Sorry about the camera in the way. That's the Fluke 5700. So we can set 10 volts and connect the cable. Let me bring the camera up. So So 10 volts set, let's operate. Look at that, we get 10 volts. I would say that's quite a progress. So, all right, let's see if we can do negative 10 volts. Okay, so at least that is working. And if we go up in range, then yes, we don't get the correct reading, because the switching is not working right. So we can check resistance perhaps. Source short, 0 ohms. So this is short. We can source 10 ohms. Ten ohms. It's not. Can't see what I'm typing. There's our 10 ohms. Given that we lost all the calibration, yeah, actually we can try. The reason why it's all lost its data, and I'm sorry, I mean the reason why it doesn't show other ranges, because perhaps calibration data is all incorrect. So let's, I think it's a long stretch, but we can just try to calibrate and see what happens. We are not risking of anything, because if the calibration is corrupted, then it's corrupted, and if it's not, then we can recalibrate anyway. So yes, let me, I never used this meter before, so yes, I need to external calibration, 0 front. Okay, so we need to connect a short. And the problem is, I don't have a short which will fit that connector probably. Let me check. All right, so let's try this one. Input high, send high. Oh, it probably will go. Or not really. Yep, it's in there. A little bit too tight to my liking, and I guess my battery died. Yeah. Okay. Have the camera battery. To fix the meter, we need to fix the camera first. All right, we're back in business. So we do first 0 front, enter, yes, calibrating, I'm not worried about the VFD. Because mostly I'll use meters over GPAB anyway, so even if it would be completely working, this unit would be still useful for me. And of course, like to do the proper calibration, you need to have the complete unit closed up, so you don't have air drafts over the analog board or all that, and have to have it warmed up for at least 8 hours. I would prefer even longer. But since now we're only troubleshooting for issues, then this is kind of okay. But never try to calibrate without doing all the proper procedures. If of course you want to have accurate meter in specifications. It's going through the ranges, 2 ohms. Didn't give any error yet. 10 kilo ohm range, 2 wire, high current mode, 1 meg, 10 meg, 100 meg, 1 giga ohm, so by seeing this procedure, you kind of start to appreciate the internal calibration function, that you only need 10 volts and 10 kilo ohm and the zero short to do the full calibration, because otherwise with the traditional instruments or even other high-end instruments which don't have the auto calibration, you would have to manually switch every range and set 0, full scale, and it's a lot of work. I can hear some relays clicking on the current ranges. Now I didn't even read any manuals or anything, because on this instrument, one of the reasons is that the manual available is all in Japanese, and I cannot read or understand any of the Japanese. But there is a big and nice thread on EEV blog forum, which I'll be definitely participating in, and that thread is dedicated specifically about this instrument. So it's on EEV blog forum in repair section, and it's already 9 pages with a lot of knowledgeable people participating in. And okay, so sorry I switched off on the most interesting moment when it finished the calibration, so I didn't catch if there was any error. What we can do next is to set 10 volt DCV. So it will ask you for the accurate output of the voltage. So we can just source the 10 volt from calibrator. And assume that the calibrator is correct, which is not really, but we don't care about that for now. We want to check if the function is working. So we connect inputs, and unlike most of the other meters, this meter have little bit strange of arrangement in horizontal way for input connectors, so keep that in mind. Okay, we set 10 volts on calibrator, output is enabled, and now we can use 10 volt signal to calibrate. And I like this confirmation that by accident you don't go into calibration and ruin your meter. It's an extra calibration step. So now it will calibrate its own LTZ reference 7 something volts against external known 10 voltage, and then do the proper calibration for all the other ranges. So DCV voltage 10 volts. If this step is successful, then we will see perfect 10-0-0-0-0-0 on DCV voltage, because the calibrator source and the meter, they are adjusted to same point. And either that 10 volt level is correct or not, that's completely different story. Once I get it all working and no problems, then I'll use my already in spec and calibrated 3458As and key 2002s to give it proper calibration. It's calibrating 100-volt range. Still calibrating. It takes longer for high voltage ranges because there is some time required to have the voltage divider to warm up. And do an internal temp calibration, whatever that means. Okay, there is no visible error. Now we can do the ohm calibration. So for that I'll have to use more probes. And I think I'll use my secondary 10-volt standard. Let me get it. And I'll use some Bosch adapters to connect my 10 kilo ohm resistor in 4-wire to those banana jacks. I hate banana jacks, so maybe I'll replace them to proper binding posts at some point, but that definitely is not today's video agenda. So let me just connect everything to adapters. Of course, I could also use 10 kilo ohm from calibrator, but well, that's fine. So we have that's the force, and now we need to connect sense. For 10 kilo ohm you need 4-wire connection, so the cable resistance will not affect your reading. That is important. It's not important when you're talking about couple percent accuracy, but when you're going for high precision, like this meter definitely deserves, you need to affect all of the possible sources of error. So there we have it, connected our 10 kilo ohm. Let's go enter the value. So this should be 10 kilo ohm. It's 9. Oh, all right, good. It's 999. 4 9s. 847. 847. This is what this resistor is, likely, given the temperature at 22°C, and right now in the lab is around 23, but we can ignore that for the purpose of this test. Enter, and yes. Now it's clicking through relays. I'm not sure if it's correct, but I think it is, because probably it will use the offset compensation to correct the thermal EMF errors. And normally you would spend like maybe 5 minutes after you connect everything to get the cables and the jacks and everything at the same temperature, so you have less error. And of course, as soon as I will power the unit down, then the old calibration, whatever it will do, it will be lost, because battery is dead. So this is just for purpose of the testing. It's likely will still fail, but maybe I was right, and maybe actually missing the calibration data will make the unit go crazy like that, switching all the ranges and doing overflow things. I'm not sure. I guess we'll find out soon enough. Okay, so it's seemed to finish everything, and I'm not sure what you do next. Exit, exit, exit. Maybe I change the data. Or it should ask you to input the calibration date, I think. Maybe not. Let's see what's the time now. Yeah, so it's all reset because the RTC is not working right. Alright, so this is 10K, and it was not working right before. We can try 4-wire. 10K, look at that. How about higher? 100K working, 1 meg working, 10 meg working, 100 meg working. This is 1G, 100 ohm overload, 2-wire, down, up, 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 up. Okay, DCV should read 0, down, 0. This looks very promising. 1 kilovolt, all zeros, current. All looks very good and promising. Let's connect it back to calibrator. And you can see when I see like when nothing connected, you can see the voltage is climbing up. That's because of the very high impedance of this meter. Many other meters of long scale have this function too, because you don't want to have meter corrupt your circuitry signal by adding extra impedance. So most of these meters, they have 10 volt range and lower ranges as very high impedance. So their input impedance is like giga-ohms and hundreds of giga-ohms. So I connected the calibrator and it's going down. It's calibrator in standby. So I'll press operate. Now we should get perfect 10 volts. And yes, indeed we have it. So we can set the resolution. Let's see, where is the resolution? I think maybe configure DCV. Yes, integration time. You can set 110 PLC. And PLC is the power line cycles. And digits, 8.5 digit. Protect, what is protect? I don't know what is protect, so we will leave that for now. And ratio, this is to do the ratio measurements for front and rear, I think. The very good function. So there we have it, 10 volts. Let's see if we get 1 volt correct. So we go range down. Should read overload, yes, and set 1 volt on calibrator. Oh, and there we go. It will take a little bit, yep. Look at that. That's a lot of digits, is it not? Let's try lower ranges, high 100 millivolt. That's pretty close to 100. Let's go range down. Indeed, it is working. Let's go range up, up. And let's go to 100 volt. Volts. Where is the here? Operate. Indeed, we have 100 volts. Let's check if the higher voltage working. Higher voltage range. $1,000. So looks good. Let's go back to the safe voltages now. 1 volt. Let's try current, shall we? We can try DCI and auto range. And now it goes very, very fast to 100 nanoamps. It's much faster than 3458A. And it doesn't do any crazy stuff like clicking, switching. You can see it's very fast meter. So let's try 1 milliamp. There it is. And source 1 milliamp from the calibrator. 1 milliamp. Operate. Nope, compliance exceeded. So Probably the fuse is broken. We can check that. The fuse right in there in the front. Let me get something to take it out. Okay, this is non-transparent fuse. Let's check with the my Fluke DMM. The standard size, 5 by like 15 or something. And yes, fuse is okay. Fuse is okay. And this is, yes, this is DCI indeed. So yes, calibrator doesn't like it. Let's try other range, up. Nope. Seems like none of the current ranges work. Let's try 10 microamp. Oh, my bad. Calibrator have two current outputs, so one is AUX, one is normal, and AUX use different terminals, so I am very sorry about that. And yes, it's all fine. There is no problem with the meter, and it's indeed working. So we can try 10 milliamps, for example. And yes, it is okay. So what we can do now is just to check if it's passed the self-test, internal self-test, and then we can call it. That's it for today. So let's check the self-test. Menu test. Enter, running self-test. Do all the clicking. That's it. No any message. I guess it's good, because otherwise if it were any error it would tell us. And it shows internal temperature, because right now it's open, so it's cool and nice. And all looking nice and happy. So we can just finish this with 1, 2, 3, 4, 5, 6, 7, 8 volts. Well, it's almost that. We can adjust it a little. I need to go. A little bit more. There we go. Isn't she beautiful? Well, and yes, we can confirm that everything will be lost after I power cycle. So turn it off, turn it on. Maybe she'll be alright. Maybe the calibration actually stored in the separate location. Let's try other ranges. Up, up. Well, this looks alright. Let's check to wire ohm. Let's source 100 mega ohm. Down. 100 mega ohm. Yes, well, that's about right. Given the connections and cables and everything. 100 kilo ohm. Uh-uh. 100 kilo ohm. There you have it. And 1 volt. 1 volt. Sorry, go back. 1 volt. It's all good. All looking good. So I think that's it for now. And as usual, thank you for watching and hope this was interesting. Bye bye.